I'm sensing a theme here. We've had water on early Mars, water in the atmosphere of Jupiter, water at the poles, and now we're going to talk about water coming out of a very small moon of Saturn. So Hunter Waite, our next speaker, is at the Southwest Research Institute in San Antonio, also, where he is the Program Director for Mass Spectrometry in the Division of Space Science and Engineering. Hunter specializes in the use of mass spectrometry to study solar system evolution and astrobiology. He led the development of an instrument that flew on the Cassini spacecraft that recently tasted the geysers spewing from Saturn's moon Enceladus. He's going to tell us all about that.
Thank you. Thank you, Louise. This is just one result from the Cassini mission, the Cassini-Huygens mission that just ended in September. It went on for many years, and there was a great period of exploration of Titan, Saturn, the rings, and many of the moons. But I want to talk specifically about Enceladus Ocean because this is one of the really exciting results that happened that we never expected before we launched this spacecraft. This is a very good example of Scott's exploration of the solar system and how it leads to serendipitous discoveries that are really interesting. To get a perspective on Enceladus, if you were to cut it open and flatten it out, it's about the surface area of the state of Texas, so it's a very small moon. It's got a density of 1.6 grams per centimeter cubed. Water is 1, so it's rocky in the center, and it's water on the outside. So let me see if I can go to the first slide. Okay, so first of all, we're going to talk in particular about habitability, and I want to concentrate on that because that's one of the interesting things. Habitability is about the ability to support life. And so there's 3 criteria that I'm going to examine for Enceladus. One is extended regions of liquid water. Another is conditions favorable for the assembly of large molecules. And the third is an energy source to form from metabolism from life. All right, so here's a picture of Enceladus. You can see some of these tiger stripes. The tiger stripes are rifts that they're cracks that actually, as we have found out over the course of 22 flybys, go and actually go into an interior ocean. And that's a global interior ocean. So by a series of gravitational measurements, tomography, and measurements of libration from imaging, we can tell something about the structure. It has a core density of 2.3 to 2.5 grams per centimeter cubed. It's got a core radius that's about 200 kilometers. It's got water plus an ice mantle that's about 60 kilometers. And so the ice thickness varies between about 10 and 25 kilometers. And that's what you're seeing on the outside. And then in the interior, or inside of that, there's a region of liquid water that is global. So that extends across the planet, and the ocean has a thickness of about 25 to 30 kilometers. So it's quite a bit of water. And that water, since in these cracks, the water from the ocean sees the vacuum of space and expands to form plumes. The plumes we actually see are ice grain particles that freeze as they move up out of the ocean, and gas pushes them out. So we see these plumes, and we see them coming out of these tiger stripe regions. So we're able to directly access the ocean. And in that regard, just to contrast what we're being able to do here. So from the remote sensing, we can gather the structure of the atmosphere. I just talked about gravity. I talked about visible imaging. We've looked at the infrared emissions from the planet. We know that the tiger stripes are hot. They indicate heat from the interior. The heat is coming from tidal dissipation. The orbit is not quite circular. It has an eccentricity that allows the forces from Saturn and its moons to provide tidal forcing that leads to heating. So these remote sensing measurements have established the kind of macroscopic view, but you have to have very sensitive instruments like this Cassini dust analyzer and the ion neutral mass spectrometer, which I'm responsible for, to look at the details of the chemistry. And that's one of the things that I want to concentrate on in the rest of the talk. So here's a picture of the interior. There's 4 bullets here that talk about some of the heat dissipation goes on deep in the rock itself. Some of it goes on in the ice. And what we've learned is that there are salts and bicarbonates that indicate salinity in the ocean. There's organic compounds, there's silicon dioxide nanograins, and there's H2. So I'm going to go through each one of these in turn. So these are measurements from the cosmic dust analyzer that shows that the grains of ice that are coming out that are about 1 micron in size, at the core of those grains, you can find the salts of the ocean. And this shows you that it has sodium chloride, bicarbonate, and we can from this determine that it has a pH that's basic about 8.5 to 9. So we can probe the interior ocean, the pH characteristics, and salt salinity characteristics just by looking at the ice grains. We can also look at the gas material that's coming out. This is a spectrum from the ion neutral mass spectrometer that shows it's color coded just to make it a little bit easier to identify the compounds. The primary constituents, and I'll come back to this, is water, but there's also methane, there's ammonia, there's CO2, and then there's a whole host of what would call organic compounds. And so the C number just tells you the complexity of the organic compound, whether it contains 2 carbons or 3 carbons or 4 carbons. So this is as far as our ability of our instrument to extend in mass. So the complexity extended up to several hundred U. So there are very complex molecules that we found in this mixture, and some of them were in the grains, and some of them were in the gas itself. So this is a short summary of composition. So I've already indicated the salt content of the ocean came from CDA, and then here's the percentage content of the gas phase. You can see that the predominant constituent is water, and then CO2 followed by CH4, NH3, and one of the things that I'll come back to because it's very important is native hydrogen that is being produced internally. One of the things that happened fairly late in the mission is that the cosmic dust analyzer was also able to see these silicon dioxide nanograins. And experiments on Earth demonstrated that they had to come from elevated temperatures. They had to be formed in hydrothermal systems that no doubt existed at the bottom of the ocean. And that, along with the measurements that we made of the H2, which was formed by the reaction of water with minerals in the interior, and that formation of H2 then could serve as potentially as a feed source for the microbes themselves. And this is analogous to hydrothermal vent systems in the Earth's ocean, like Lost City. So we think that there are hydrothermal systems. We have a couple of pieces of evidence indicating hydrothermal systems that are at the base of this ocean and that are producing very interesting chemicals that are important in supporting life. One of the reactions that we studied was what methanogenic bacteria use the reaction is represented by this 4H2 plus CO2, but basically molecular hydrogen reacting with CO2 to form methane and water. And this is a food source for microbes in the hydrothermal systems on Earth, for methanogenic archaea, excuse me. And this figure, which is a little bit with a diagram itself, which has a few lines across it, shows you that there is positive energy, positive chemical energy in the system that we can measure that microbes could use and could eat. So if you put a microbe from Earth in this system, it would live. Whether they exist is still a very open question at this point in time, but we know that the chemical energy in the form of molecular hydrogen is there for these species, for these potential microbes to eat. There are other potential sources of potential metabolisms that might take place, like anaerobic oxidation of methane and sulfate reduction. In this particular case, the formation of the sulfate comes from the fact that you form O2 from radiolytic processes, from energetic particles on the surface, and then you eventually bury that in the ocean, and the O2 forms, it actually forms the sulfate. So we know that there are several different ways to supply energy to this internal ocean, and we certainly are quite interested in trying to pursue whether it actually supports life or not. So to summarize, we've looked at the internal structure. We determined from those measurements that there is a global ocean, that it thins in the South Pole where we see these plumes coming out. It's pretty close to the surface. The water comes up in these cracks to probably 4 kilometers below the ice surface, so quite close to the surface. We know that the interior ocean has a pH that is basic, that it has salinity characteristics that are similar to the Earth's ocean. We are fairly certain that there are hydrothermal systems, like on the Earth, in the Earth's Atlantic off-axis ridge, Lost City, that can support life. And we know that that the chemical constituents that would support microbial activity exist there. So it satisfies all the criteria for habitability. And so the next step is really to go back and search for life. And finally, just to say that this is not the only moon in the solar system that we suspect where interesting things like this may be occurring. One of the next steps we're going to take, a NASA mission called Europa Clipper, and we're building a mass spectrometer to fly on that mission to take measurements at Europa, and we'll hope that we'll be able to make similar measurements about the characteristics of the interior. It's not as clear that there are plumes that allow direct access to the ocean as it is in the case of Enceladus, but it is likely that we can tell something from the surface composition that gets sputtered out or outgassed that will tell us about interior. So I'll stop there and take any questions.
Questions for Hunter?
Obviously, to me, it seems obvious anyway that this is not a stable situation. It's been going on for 4 billion years or so, because you're losing mass with these jet plumes. If the plume situation is not perfectly isotropic, you have a thrust that's moving changing the orbit. So is there any way of figuring out or estimating how long this situation that you just described existed?
Yeah, well, to know how long it has existed is a difficult thing. To comment on whether the whole system would dissipate or not. We know that the oceans have to be, the heat capacity that's in them, they have to be around for tens of millions of years. So that level of stability is present. We know that the amount of material that's coming out at the present time, if we extrapolate that back in time, will not get rid of all the material. It's about 200 kilograms per second of water vapor that's coming out. So in that sense, the ocean is stable. We can do calculations that suggest that the H2 that we see could be sustained from water-rock interactions over a 4.5 billion year life period. So we don't know how far back that is extended, and we don't know the evolutionary history of the tidal heating, which is one of the important features of trying to sustain the system, is to maintain the heat source.
Thank you very much.